The first person up is Changsheng Dai. He is a postdoc with in the surgical pillar under Sun. And he is going to be talking to us about robotic intracytoplasmic sperm injection, the ICSI. Cheng-Shen, if you're here, go ahead and turn on your video and take it away.
Yes, I am, but the message is saying I cannot start my video because the host has stopped it. Could you please figure it out?
Absolutely. There you go.
Okay, fantastic. Okay, so my name is Changsheng Dai. I'm a postdoc from Professor Sang's lab. The topic I'm presenting today is robotic intracytoplasmic sperm injection, ICSI. Next slide, please. According to World Health Organization, 1 in 6 couples worldwide is infertile, amounting to 50 million couples. And a lot of them require in vitro fertilization to have babies. And the ICSI is the most widely used techniques for in vitro fertilization. It is implemented by injecting a single sperm into an egg, but the live birth rate of ICSI has plateaued around 30% over the past decades. Additionally, the manual operation of ICSI under the microscope suffers from inconsistency and undesired cell damage. To overcome these limitations, we have developed a robotic ICSI system. Here, I will briefly introduce 2 key methods to achieve less invasive cell surgeries: cell orientation control and cell injection. The next slide, please. In ICSI, the cell need to be rotated so that the polar body is away from the injection site, but manual rotation suffers from large deformation. And we have developed robotic cell orientation control with minimal cell deformation. As shown on the top right, we firstly establish, the last slide. We establish deep neural networks to detect polar bodies with robustness to variations of polar body size and shapes. Then we designed an optimal controller. By minimizing the cost function, both cell orientation error and cell deformation can be minimized. So our polar body detection achieved an accuracy of 97%, and comparing to manual rotation, our robotic approach achieved much less orientation error, maximum deformation, and operation time. This work was awarded the Best Paper Award in Automation at the conference of ICRA 2019. The next slide, please. After rotation, the cell need to be penetrated to deposit a single sperm. But this process usually involves large cell deformation. And to reduce the deformation during penetration, we develop a Piezo Drill, as shown on the top right. The Piezo Drill is mounted on a standard micropipette holder. It uses the piezoelectric actuator to generate micropipette vibration. And the flexure beams are used to guide the motion along its axial direction. To prevent the piezo vibration to stir the cytoplasm, we used updated motion history image method to detect the membrane breakage. So once the cell is penetrated, the Piezo Drill will be stopped automatically. We first tested the Piezo Drill on hamster oocyte, and the use of Piezo Drill leads to a post-penetration survival rate of 92%, which is higher than the survival rate of 77% without the Piezo Drill. Now the Piezo Drill is now undergoing a clinical trial in Hannam Fertility Center in Toronto, and the results from human oocytes show that the cell deformation during penetration with the Piezo Drill was 10 times less than that without Piezo Drill. The results are presented to the Scientific Congress of American Society of Reproductive Medicine. And with these robotic techniques, We hope to reduce the cell damage during manipulation and ultimately improve the live birth rate of ICSI. Thanks for listening, and your questions are welcome.
Excellent. Thank you. Thank you so much, Changsheng.